Okay, so today we are going to start on chapter 2. In chapter 1, we are basically introduced to the basics of the stress. What's the normal stress, what's the shear stress, and how to calculate them, and very simple design steps. So if you want to design something and make sure it's not going to fail, how we are going to design it. And then at the very end of the chapter, we learn a little bit about the safety factor and those kind of things to just move away safely from the maximum loading that any element can handle. In chapter 2, we start to look at the deformation. So if we have in statics, we said, okay, we put the load on any particle or any member, and then we just look at how it's going to stay there. Then in chapter 1 of that said, okay, if these are the load, what's the internal load, and how those internal load could be translated into the stress. Now in this chapter, we are going to look at it. If you have a load on a member, how it's going to deform, how its shape is going to change. So
that heavily depends on the material it's made out of, doesn't it?
yes, it does.
Okay.
So the first concept that we're going to talk about is strength. So if I have, for example, something that is hanging from the wall, element like this. And has a, assume it has a length of L. And then it has a cross-section area of A. If I go ahead and start to pulling that down. Okay, so just go ahead and say, hey, I'm gonna pull that down, and the amount of force I'm gonna put there, assume it's gonna be, I'm gonna call it let's call it P. So that's the amount of force I put there. I pull it down. So if it is, for example, a steel, you probably don't see much changes. It's there, but you don't see it. But if it is rubber, definitely you can see. If it is a rubber and you pull it down, it just comes down. And then you're going to have this amount of change, let's call it delta. Basically, this is the amount of that formation I have. So in this chapter, what we want to look at it is that, okay, how we are going to find this delta or what are related to that delta. Now, if I go ahead and say, you know what, I'm going to have the same things here. I double my cross-section area. Same length. So it's going to be L initially. And the cross-section area is going to be just double. Now if I go ahead and so I double the cross-section area, I'm gonna go ahead and double the forces applying on that as well. Is it gonna stretch further? It's gonna stretch less, or it's gonna stretch equal? If I, let's say 2F and the 2A. If I double the area and double the force, it's going to stretch more or less.
Less.
So it's going to stretch less, so why?
By doubling the width, you
Not the width, the cross-section area.
the cross section, the volume on the inside goes up by a higher amount, and so there's more material there, like ratio-wise, than you did by adjusting it, and so you'll need an even greater force than just doubling it to move it.
What do you think?
I was gonna say it's like the dimensions of the area are squared, so the change is gonna change by a square instead of just a multiply.
So it's going to be more or less? Less. If you do that and you go in the lab and you do it in the lab, it turns out it doesn't stretch more or less. It's gonna stay the same. So if you go in the lab and test it, so you say, I test this, I'm gonna test that. Both of them becomes delta. So basically it tells, if you go there and you increase the force and the cross-section area, or decrease the force and cross-section area with the same factor, the deformation would just stay the same. Now, so force and cross-section seems that they are doing the same, they are moving in the same direction. What about the length? So if I go there and say, compared to the first one, I go there and this time, I double the length. So if this is and keep the cross-section area the same. So the length is this time 2L. And then keep the force just F. So compared to the first one, I keep the area the same. So I keep the area the same. I keep the force the same. But I change the length or double the length. So, do you think if I change the length, it's gonna make the deformation more, less, or equal? More?
I think it's probably gonna be either equal or less. So I guess I'm betting against him.
So it turns out if you double the length, you go in the lab and you measure it, it double the deformation. So if I look at these three cases, the deformation depends on what?
A cross-sectional area or width, the length, and also the
force.
the force, yeah. Okay.
So here, if I want to somehow make that delta, it says, okay, if I have 1 meter, assume 10 centimeter. If I have 2 meter, 20 centimeter. But how can I make it more sense that is independent of the length? If I want to say, okay, what's the deformation of the steel? Someone will say, okay, what's your length? Correct? But if I want to get something that is independent of the length, so you ask me what's the deformation of a steel, I tell you, okay, that's how much the steel will deform. In general, under the certain force. That's what they call, so we are gonna go there and say, hey, you know what? We are gonna go ahead and say, something we call it strain. And instead of having that, we are gonna divide the delta by the L. So in this case, then I don't need to know how much is the length. It's just relative deformation. So I know that, for example, if someone tells me it's 10 tons, I know that, okay, what's the relative deformation of that member? It calls the strain. So that epsilon is the strain. What's the unit of the strain? Doesn't have any unit. Because it's the length divided by length. The delta is the deformation, a change in the length. And the L is the length.
Is that like an uppercase delta or like a lowercase delta? Normally, when I hear delta, I think of like a triangle. Yeah, that's like not. It's not like.
This is, I would say, the big one.
Okay.
That's a small.
Okay. So they are different. But, okay.
So uppercase, lowercase, or capital. I usually use the delta for showing the change. So in this course, always they have it, the delta, but you could have, for example, say that basically the delta is delta F. The change of the length that you have. So, but as I said, this is the length by length, but it's, I mean, it has a, it doesn't have a unit, but sometimes they represent it with the length over length. For example, it says, instead of, say there's no units, for example, it's gonna say 2 millimeter per meter, for example, because both of them are, so you have some idea of what it is. So that's the strain, and so if the, like what we had before, the epsilon, if it is positive, it is when the sigma was positive, what did it mean? The stress.
Tension.
It's tension means it is pulling it apart. So if the tension is positive, the strain is gonna be positive as well, and it means that your length is increasing, or where it has elongate. So when you have the strain positive, means that under that it is increasing, and if it is negative, means that it's shrinking or. Can have them here also, so you can have the sigma positive is the tension, and sigma negative. F divided by area, so if it is positive, it is tension, as negative, it is compression. And so it's the same. So if it's negative, means that you're compressing the element, so that it becomes shorter. Let's see, so the difference is- Now we have, look at here, we have these two, we have the strain and we have the stress. Right? Is that, how do you gonna connect these two together? I'm gonna connect the amount of force I put on the material to its deformation. Because I want to calculate the deformation, usually I have the force, this is what I have. So if I have the force, I can calculate the amount of stress is gonna be on that element. If I can calculate the amount of stress on that element, how can I calculate the deformation from there? I'm gonna know, or vice versa. If I know how much deformation my member has, I'm gonna find out how much stress applied on that to get that deformation.
There's probably like a coefficient for the material that's like, oh, this amount of, like, it's 2 times the force is this for that material or whatever.
It is. It's what is almost correct, but how we're gonna find it? So to find that is that there's no way that you can mathematically find it. The only way that you can find is that you have to go in the lab and start to do some tests to find what's happening. So the next part that I'm gonna talk about it is conceptual is very important. We are not using it much mathematically except for one number out of that usually. But conceptual that you understand what happens is very important. And it's called the stress-strain diagram. So for any type of material that we have, if we want to find out, okay, what's the relationship between stress and strain, there's a sample, we get that sample, and we take it to to the lab. And the samples are usually very, they're the standard samples, so everything is standard about Let's look like something like this. This is the images in the book. The sample is look like that. So there's a that sample part usually goes as a zip, something like this, and then there's a something like that's real good. So that sample has a known length and known cross section. It has a standard length and a standard cross section area. The both ends is gonna connected into the machine that hold the top and bottom of that, and it start to stretch it. So what happens that when it start to stretch it from both ends, it measure how much force is applying on that, and at the same time it measure how much deformation that middle part of that section, that known part of the section is gonna have. And it starts to recording it. And then it starts to plot it. For the different material, the plot's gonna be different, but the one that's the most famous one, and they're usually using it, is for the steel. Because the steel's one, figure that depending on what material you have, if you have, for example, you run that test 10 times, you're gonna get 10 different curve. But some of the material, those 10 different curves are gonna be very close to each other, very similar, like for the steel. Some material, no, you might test it 10 different times, get completely 10 different. So the steel usually, because it's very consistent, is the one that referred to a lot. So if I go ahead and draw the shape of that, so I say, hey, you know what, I'm gonna draw the stress that I'm gonna get here. So that's gonna be my, and here, space. Gonna be pixel. So I'm gonna draw them like that. I'm gonna run that test and start to measuring it, see for any deformation how much force I need, or for any force how much deformation I get. And if I draw it for the steel, this is usually what I'm gonna get. So it goes relatively sharp up there, and drop, become relatively horizontal, goes up, and breaks. So there are some parts into that. This section, the slope is steeper, is up here, so I just drop it a little bit so I can show you what I mean. But usually it goes very sharp up. This section of that, let's see. this section of the graph, they call it the elastic section. It means that if the material is in this section, they have the elastic properties. This part is the plastic section. So what's the difference between elastic and plastic section?
Elastic, it'll go back to its original form. Plastic, it won't. Like it's deformed, but it's deformed to a point where it can't go back to its original, where its properties have now changed permanently until you can like melt it back down and whatnot.
So the elastic is that any deformation can be, if you remove the force, the deformation will be eliminated. Like if the have the stretch band or something, you stretch it and let it go, it goes back where it was. But the plastic part is that if you stretch it, that deformation is going to be a stay there. If you leave the force, it's not going to go back to where it was. So it's going to be the permanent deformation into that into material. So that's two part of that we once the to this section, and then from this section to this section, from this section to this section. So look at here, the sections that I have, it goes up, goes up, goes up. Right here, if I put the force, if I increase the force, the deformation increase. Increase the force, the deformation increase. Increase the force, the deformation increase. Okay? Until I reach a point here that they call it the yield strength. And that yield strength, so if I come here, that call it the sigma y. And it's called the yield strength. Until I get to that point, the yield strength. Okay? Forget about that little tip there. When I get to that point, if I start to stretch it further, the force doesn't increase. So the force stays there, and when I reach to that point, so basically I increase the force, increase the force, increase the force. When I reach to that point, without further increasing the force, it just keeps deforming, 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 deforming. So up to here, if I want to increase the deformation, I have to increase the force. Increase the force, increase the force, increase the force, increase the force, increase the. I get to the point that I don't need to increase the force any further. It just keep stretching, 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 stretching. Without I'm doing anything. And that's the yield section of that, called that part, the yield section. section, call it the yield section. Until I reach that point here, when the deformation get to that point, suddenly it starts to show resistance. So, look at here. The material get to that point, suddenly it stops to show any resistance any further. For some reason, they still don't show any resistance. For the same force, you just keep change the length, change, until you get there. When you get there, suddenly it still goes back and it starts to show the resistance, and then it starts to increase up to here. This section, they call it hardening. So basically, after just do nothing, suddenly it starts to show the hardening, or they call it the strain hardening. Until I reach that point. That point, what's that point? It is the ultimate strength. Is the maximum that the steel can handle. Let me redraw that. When I reach to that point, if I go and look at my sample, there's something happened to my sample, and the sample starts to look like this. Sample starts to look like that. The middle of the section, of the sample starts to become narrower and narrower and narrower. See that? So here's the same, here's the same. At the very middle of that, it starts to become narrower and narrower and narrower and narrower until it snaps. Until it will break right there. This process is called necking. That part that is going to start to become smaller and smaller and smaller, and it happened here. In this section. So this is this necking, or basically when the very middle section of that element starts to narrow, happens from this point up to this point. And what is that point? Sigma B for the breaking strength. you said, those yield strain hardening and the necking happened in the plastic section of the diagram. But we don't have any of them when we are dealing in the elastic part of it. So, this is for steel. This is the breaking diagram of the steel. So, where we want to be as engineer, usually we want to be right here. We don't want to get into any plastic part of the diagram. Yes.
Isn't there a process called like hardening or like steel hardening that you do during like a forging process? Would that affect this diagram at all? Or
Anything that you do, this is the diagram for the
raw steel?
no, the steel they're using mostly for the construction material. If you do any change, a very simple change in the production of the material, it's gonna give you completely
Okay.
different care. So, if I go ahead and look at, if I change the material to another material, so the next one that the book has is the aluminum. If I go say, okay, what happened to the aluminum? So I'm gonna draw it here. And I'm gonna, the sigma here is trained here. And go ahead and draw what's happening to the aluminum. Again, we are going to have the elastic section, but this part of the steel is not there. It goes from here right to here. So you don't see this yield part in the aluminum. So it goes there, and then it goes like. And breaks there. So the part that is going to be linear, this linear part, that's going to be the sigma y. U, and then we just sigma v. By the way, these magnitude, they are not in the same scale. These are going to be much less than this too. So I'm drawing the same scale, but for example, the usual is going to be small. So that's what happens if you have the aluminum. So, like here, the steel and aluminum, what type of material they are?
Metallic or metal?
Yeah, they are both. I don't know how to explain it. There's no way that I can explain it. Is ductile?
Yeah, the
So, what's about the ductile material?
Tactile bends, and it has that elastic period. Or ductile.
No, the other ones also has the elastic.
Oh.
The main characteristic for that is that it can deform largely before it breaks. So if you look at here, there's a long deformation before it actually break. So it can large deformation before breaking. So why is this good or why is it bad? It is a good thing. Usually in the engineer we prefer that.
I mean, it's good because it has a large deformation before breaking, so like it gives a longer like warning period, or you can see that it's about to break, basically.
That's exactly right. So basically, you can see it's gonna break. You can see it is gonna fail. So for example, if it's a building and there's a beam, you can see the beam is bailing, also the beam is bending down before it break. You can see it gives you time to get out of there. If it is not, if it doesn't show that, you don't see any sign and suddenly it snap without giving you any sign. So that's usually one of the good things about it. But another point about them is that when they break, look at here, the necking. If I have that, when it snaps, when it breaks, breaks like that. So it breaks at 45-degree angle. If you measure it is exactly 45-degree angle, that the part that it snaps, if you look at it, it does look like this. Breaks at 45-degree angle. So what the 45-degree angle breaks telling me? What that telling you? When we were talking in the last chapter about the 3D stress and strain, what between the normal and shear, which one was maximum at the 45 degrees? Shear become maximum at 45 degrees. Because look at it instead, if I put the force on that, it's a completely axial force, correct? So basically what I have here is just axial force pulling it. So under axial force, I get the 45 degrees break. On the axial force, the shear becomes maximum at 45 degrees. So it means that shear is responsible for that break, not the normal stress. So that it might not feel right, but you can look at it and say, hey, the steel, if I pull it away, if I put it under the steel, the steel will break under the shear, not under the normal stress. That's completely against what you feel it should be, because you're pulling it apart and say, okay, if I'm pulling it apart, it should break under the pulling or the normal stress, but no. The steel doesn't yield under normal stress. It breaks under the shear stress. So it means that shear stress is responsible for breaking. Any question up to here? This is very important. Remember that we will get back to this later on in the book. That it breaks at the 45 degrees, and when it breaks at the 45 degrees, it means that the shear is responsible. Now if I go ahead and draw the same diagram for the any brittle materials, so the typical brittle materials, if I go ahead with draw this. The diagram there. Epsilon. Usually, so that's the general form. Almost all the material is going to look like this. So it goes like and it and the thing is that the sigma u is the same as sigma
expected it to be almost the beginning of the steel diagram and then just drop off like you intended it for.
So as I said, I tried it a little bit exaggerated, but if you want it, it's very small here and boom, it will breaks. So for the brittle material, if I want to talk about it, is that this is typical brittle material. So typical. So if I have so the brittle material breaks suddenly under stress without showing noticeable deformation. So what's the example for the brittle material that we use a lot?
Wood.
What's that but another one?
Drywall. Concrete.
Concrete. Concrete is the material that you're using it a lot. And it's one of the problem with the concrete is that this material, if it fails, it fails. It never gives you any sign. You're there, suddenly the entire building comes down. Now, similar to that, if I go ahead and again like this and put it the pressure on that. So if I have it like the material that I have, so it's gonna be look like this. How do you think it's break when I pull it apart? It's gonna break like this. That breaks at 90 degrees. So what does it mean? And it says it breaks at 90 degrees.
It's the normal force that breaks it.
Normal force is responsible. The normal stress is responsible for breaking it. So the steel will fail under shear, the concrete will fail under normal stress. Any question up to here? So all we have here was under tension. What if I put the same sample there instead of putting the part, pushing it, compress it?
Concrete does a lot better, I'm pretty sure, under compression than it does.
Concrete doesn't do much under the tension. Usually the design you completely ignore it, you say okay, it's just useless under tension. But it does really, really good under the compression. So the thing is that some material, some material in the tension and compression they behave the same. Some material completely behave differently when it comes to the compression. So let's go and look at some of the properties if we have compression. Some of the material behave very similarly on the compression and the potential good. For example, the steel behave very the same. Either you compress it or stretch it. But the concrete does different. So here I'm going to draw the one for the concrete. Epsilon. Like this, but I can't draw it. So why this part is below the axis?
Because the strain is negative.
Yes. Because the stress is under compression, the stress is negative on the tension. So the above the axis is tension. So if you are up here, it's tension. So here is tension. It's compression. Remember, the tension was positive, the compression is negative. So that's why we tried and do that. As you can see, that's for the concrete. And then see here, under compression, you can have the sigma u. So it's a sigma u under the compression, and then you have that sigma b for compression. That is the sigma u for compression. And then you have, again here, you have sigma b for tension. Concrete. And then there's an elastic range, so it's going to be, for example, from here to here. So these part are the elastic range. So it behaves elastically within that part, then it's become plastic after that. Couple of points, for example. For a steel, yield stress is the same in both tension and compression. So it still behaves similarly under tension and compression. Next is for brittle material. For brittle material under compression. For brittle material under compression, these 2 points are only valid if they are under compression. Elastic range is larger. So look at here. The elastic range under compression is larger than the elastic range under tension. It's larger than under tension. And breaking or rupture does not occur suddenly. So if you look at it, it goes and then it goes under plastic deformation, large plastic deformation before it breaks. But under compression, under tension, no, it doesn't show much deformation before it breaks. Under compression, these points. We have ductile material behave the same as under tension until the end of strain hardening. So remember, it goes to the strain hardening and then the necking. Except for the necking part, everything else is going to be similar for ductile material, either tension or compression. So basically, they behave the same. They're only different in that necking part. And under tension, we have that it becomes thinner and thinner and thinner. Under compression, that doesn't happen. So basically what we have is that ductile sigma u under compression exactly the same for the sigma u under tension. For brittle material, no. Under compression, the sigma u is larger than under the tension. And this is here is just this is also the sigma u. Same. And the last point that I want to mention is that for both I will tell you what it is, but postdoctoral, and the elasticity modulus is the same in the tension and compression. I will tell you what is that E in a minute. I will tell you what's the E, but E in the tension and compression is going to be the same. One thing is that when for the strain and strain diagram, when you're dealing with that, when they want to calculate the stress and strain, they use the original cross-section area. So if the cross-section area originally, for example, here, if I have that, if this cross-section area is A naught, so they calculate the sigma is equal F divided by A naught throughout the entire calculation. This is how they do it. But in reality, we know that when we stretch it, it's going to become narrower and narrower and narrower. So the A is going to become smaller and smaller and smaller, correct? Those curves that I draw, and that is what the engineer using it. We assume the cross-section area stay constant, doesn't change throughout the process. But if you go and consider the change in the cross-section area, that's something else happens, so you're gonna have something like this. So if this is the original one, it goes up. The true one is gonna go like that. The true one goes like the same as this one, comes here. It'll look like this. So that's the true fracture stress. That's the fracture stress. As you can see, they're gonna stay the same until here, and then they're gonna be different, correct? In engineering, we usually just care about this part, the elastic part, so that's why we don't care about that's what's happening there, because we usually want to be there. We don't want to be anywhere close to that. But just know that if this is the real one, this is what we are calculating, assuming the A stay constant throughout the process. Now, Hooke's law. Okay, this is the sigma, the epsilon. If I draw that sigma epsilon things again here. And then I go and draw it. The slope of this line, the slope of the line of elastic line, we call it E. The slope of that line, we call it E. If the slope of the line is E, what would be the equation for that line? The equation for the straight line that goes through 0, 0.
Y equals mx plus b.
And B is,
Just 0, so it's just y equals mx.
so Y is equal to mx. What's the Y? Sigma. What's the X? Epsilon. And what's the M?
E.
So sigma is gonna be E
Epsilon.
epsilon. That's the Hooke's law. So sigma is equal to E epsilon. So remember that that's only correct for the elastic part of the curve. And that's where, as an engineer, we, as I said, we care about it. And then E is the modulus of elasticity. And usually they call it the person who did it is the name of the person, Young modulus. Very often they call it Young modulus, but so remember that either they call it this one or the other one. What's the unit for that? What's the unit for epsilon? Nothing. So the unit for that should be the same as the unit for the sigma. So it's going to be either Pascal or pound per square. So the unit for that is going to be either Newton per square meter or pound per square inch or anything, any stress unit you have. That's a very important formula. That's the one that I said at the very beginning. I said, if I know the deformation and I want to show how much force caused that deformation, that's how I can find it. But if I have the force and I want to know how much deformation is going to cause, that's the equation I'm going to use. So basically, if I know the force and find the deformation, or if I have the deformation and want to find the force, equation that we are going to use it over and over in almost all the problems. In many problems we are going to use. Any question? There one more section left. That all I was talking about up to this point is that loading. What happens if I unload? If I load and unload, load and unload, then what happens? Then if I do the unloading, first the simple unloading, what happens if I just simply unload?
If it's still in the elastic period, it will go back to its original shape. If it's not in its elastic period, of course, it'll stay in its deformed shape.
So elastic versus plastic. Before I tell that, there's one other thing I remember. So in the concrete, why do we put the bar?
Its bending is terrible because when you bend it, you're putting this middle section under, like you're stretching it, and so it snaps really easily. And so the rebar is there to add to strengthen it in that way.
So it's both for if it's bending or if it's just tension. As I said, because the concrete doesn't do anything. We assume it doesn't do anything at tension. So we add the bar. So when it's compression, we assume the concrete take care of it.
Mm-hmm.
But for any reason it goes under the tension, then the bar is going to take care of what's happening. So if I have in my normal and epsilon, and then I go ahead and say I'm gonna have like this. As I said, because the steel is one of the best behavior materials, so usually we use the steel. If I put the load up to here, if I go and put the load up to here and remove the load, what would happen? It will goes back to where it starts, correct? So as long as I'm in the elastic part, if I put the load, it will goes back to where it starts. But if I go ahead and say, hey, you know what? I want to put the load further than that. If I go ahead and put the load, for example, up to here. Then what happened? The elastic part is always goes back to that part. So that elastic part is always goes back. Which part doesn't go back?
The plastic.
Plastic part. So it's gonna go back parallel to the elastic to where I started. So if I, for example, it doesn't matter, go up to which point. So it goes back parallel to that. I try to draw it parallel. So it goes back. So the elastic part, you see, this is the amount of the elastic part. The elastic part will return, but the plastic part will stays there. Now, if I want to put the load on that, where it's gonna start? If I again, so it goes up there and comes back here. So it comes back to no force. Now if I put the load again, what happened?
Will it take that line basically straight back up?
So from here or here?
From there.
So it's gonna start from there. So it goes from there. If I reload it, it goes from there, and then basically follow that curve. So that's the plastic deformation that's gonna be there forever. So if I load it and go to the plastic part, I never can get rid of that plastic deformation. And there. Another thing is that if I load it, that's the original one. So assume I go ahead and load it up to here. So I go up and load it here, and then go back down. I get here, correct? Now, what if I start to pushing it instead of here? I pull it apart, I come back down, and then again start to pulling it. What if I go there and start to pushing it?
It's not going to go back to its elastic form. It's just going to.
Depends on how much I push it. I can push it up to here, then it goes there, and then I can unload it so it can goes back to 0. But is these two materials gonna behave the same? So even if, so you can not, even by loading it, so by compressing it, you cannot get rid of that plastic damage that caused to the material. Okay? So it's going to be always the same as it was. So now if I, no, let's assume we are not. is. I don't want to get confused, so I just want to go back down. Come back here. Come back here. And I go back up. It goes back here on that curve, eventually here. And it starts to move from here up. If I do again, start to remove it. Remove the load. It will go back down. And again, if I put the load there, again, it goes back up. So I can keep loading on tension, compression, tension, compression. So remember that this is tension, this is compression. One thing that happens is that the distance between how low you can go and how high you can go in every cycle of loading and unloading is always 2 sigma y. So this distance here is 2 sigma y. Regardless of how far you go up, you always, the distance between the highest point and the lowest point is going to be 2 sigma y. And remember that is our sigma y here. That point. And 2 points, because I'm going to write them there. There's a creep. You know what's a creep? If you put the load for a very long time on the member, even in the elastic section, the deformation will be stays there. So even if we are in the elastic section, if we keep the load for a very, very long time, it never goes back to its original shape. So that deformation will be stays there. So when a member supports the load for a long time, continue to deform until sudden fracture occurs. So the creep is the time-dependent permanent deformation. So in other words, if you have a stretch band, stretch it and leave it for 2 years. After 2 years, if you're gonna release it, it never goes back. You are in the elastic part, but it never goes back. If you stretch it even further and keep it there for 2 years, it might just snap. So that's a creep. The next one is the fatigue. material
Still here.
subjected to repeated cycle of loading. Structure breaks down and lead to fracture. You might know that if, for example, you have a piece of wire, assume you have a piece of wire bending, eventually to break. So any type of material you have, if you start to load, unload, load, unload, load, unload, load, unload, after certain times of loading, unloading, it will break down. So it's not that we look at this and say, okay, this is the yield stress I have, and I can use it to put it in the cycle of 2 million times or 3 million times of loading, unloading, loading, unloading. It's going to break much faster than that. That's the fatigue. Any question?